All right, how's it going, everyone? We're back working on this lightsaber some more. And tonight we're going to be, I think, finishing up, or trying to finish up the speaker. And I don't know what else needs to be worked on, honestly. So, yeah, there's going to be that. All right, so let's get started. As usual, have the same bounties going, so if you want them, if you want any Dogecoin, try and fill those. But let's get moving on this. So last time I ended up finding a breakout board, this one, with a speaker on it, that seemed pretty straightforward, just required a power ground and then a data line, really. And I need to find the schematic for this. Here we go. Somewhere in here, I know that we had it. Yep, here we go. So, I can figure out the chip. This is what I need right here. Okay, so I figured out what this chip was and decided I think it was either too small or I couldn't get it in stock or something. But I picked up something similar that I'm going to use. The only thing is, right here, we have this voltage divider of sorts that we can use to adjust the volume. And so I need an SPI controlled potentiometer effectively to do that. And that shouldn't be that hard to. I say it shouldn't be that hard to find. It should. That seems like something that should exist. So I will see if I can find some. Here we go. Programmable potentiometers. Active. Tray, cut tape. I guess bulk and strip as well. That doesn't change anything. Okay. So we need to find something that's going to be easy to use, either through hole or really big type of pinout. And I honestly don't know what all goes into all this stuff, so can I select based on the minimum quantity? That's better. Okay. Oh, there is some through hole stuff. Okay, that's interesting. SPI. Ooh, this looks really interesting. Let's see what we got here. Server error while processing request. That sounds about right. Oh, it takes me to a microchip link. That's why things are going wrong. All right, let's just search the part number. Eight-bit single digital potentiometer with non-volatile memory and SPI. That's interesting. So it probably retains its state after you turn it back on. Like you turn it off and turn it back on. So we're looking at the 4161. Do they have different package options? Is that a thing too? Yeah, they do. DIP, SOIC, MSOP. Okay. Five. Ugh. Excuse me. All right, I think this will work. I just gotta, let's see here. Supply voltage, we can do 3.3. Oh, wait, hold on. Okay, I need to figure out what this means. Serial interface only, 1.8 to 2.7 volts. That's odd. Oh, it might be like, Nope. Alright, that's kind of weird, but we'll keep looking here. Okay, so if I look at this, effectively what we got, caps there, small resistors, just 100 ohms each on our inputs. That goes directly to the speaker and back. And then we have Steve video, ground. Interesting. To see what my circuit has. SDB and bias. I need to figure out what those are. All right, I have the ROM chip pulled up. This is going to be a whole adventure. SDB is the shutdown, so that's useful for that. I need to figure out what the current usage of the potentiometer is as well. Maybe it has a shutdown mode, because that would be ideal for keeping it from using too much power. I don't know what the bias does, though. Okay, this SD is probably also a shutdown. I probably need to be looking at this chip datasheet too, just to see what's specific to this and what's specific to the other one. Let's see here. PAM 030 2AA SCR. That's not right. 030 2AA SCR. Interesting. Oh, well, here's the data sheet, supposedly. Okay, yep. Let me go back. All right, what are the different pins for? So the shutdown, I think, is probably the same as on this one. But I need to learn what all the other pins are. Interesting. They recommend a ferrite bead there too. That could be useful, actually. That's good to know. I'll have to look into that. All right, I'm assuming SD is shut down. Yep. But what is the other? Oh, minus. What else is here? It's VDD ground, shut down, and minus not connected. Okay. Pin 1, pin 2. And what is it here? Pin 1 is shut down. Pin 6 is VDD. That's where that is coming from. Okay. 2 is not connected. So I need to, okay, so that's pretty straightforward. So I need to figure out what the bias is because that's the extra pin on mine. What does that do? I'll give it a second. There we go. Bias, just capacitor to ground. So it probably isn't used for anything in particular. Interesting that they don't recommend a resistor here as well. I don't know what this is for. On the block diagram, it's part of the shutdown pin. So, interesting. This kind of shows the circuit too, which is cool. Influences audio characteristics such as these. Locate low ESR capacitor close to the bias pin. Determine capacitance of C1 including the range below, including variation temperature characteristics. Also, turn on time and turn off time are also determined by the capacitance of the bias pin. For the following section, turn on, turn off. Okay. Interesting. So I probably just need to connect it as shown, but it should be fine otherwise. Do they recommend on this a ferrite bead? They do not. Though I could see that being a good idea, I guess, to eliminate any kind of unwanted noise on that line. And the caps could do it as well. I might do that. I guess I don't have to populate them, or I could populate them with something weird. Like something different than the values suggested here. Bead. 220 picofarads on each side. That's pretty small. I thought I saw another one in here, but maybe not. So just that. Okay. Well, that's doable. We could probably do that then. All right, last thing then. So I think this is going to work. We need to figure out if this potentiometer is going to work, though. All right, supply current. If the serial interface is inactive, is low, but if it is active, 450 microamps. It's a lot, but not terrible. I don't know if there's like a shutdown mode or something. What's the pinout on this? Chip select. That makes sense. Clock, SDI, SDO. Serial data in and out is on the same line? That can't be right. Okay. SDI, multiplexing. Well, how does that work? For these dual ones, it has a shutdown pin. It doesn't look like it has it for the big ones. And maybe I need to be using a rheostat. What's the difference between a potentiometer and a rheostat? I don't know that. All right, let's see what I can figure out here. Difference between a potentiometer and a rheostat. Drag. Shortly designated with the letter N. Hold on. Oh, rheostat just it basically is a variable resistor, versus a potentiometer is more of a variable resistor divider. Okay. Voltage divider. So we definitely do need the potentiometer. I don't want to use one of the big ones because I think that's kind of excessive, but might not be able to get away from it. Well, there's a lot of control lines on those two. But I want a way to shut it down. All right, maybe I can find an example circuit in here. Wow, there's a lot to this data sheet. Oh, okay, here's an explanation of this. Pinout limitations do not allow for individual SDI, SDO. On these devices, those pins are multiplexed. It knows when the pin needs to change from being an input to being an output. The host controller's SDO pin must be properly protected from a drive conflict. So I'll have to set up some sort of circuit, basically, to handle that. I'd rather not do that. It's a lot of extra, a few extra parts, but okay. Let's see what else we can find. Maybe we can find something better. Let's see. Let's go for a 10K. That should be common enough that we have a few to pick from. Then wow, some of these get really expensive. want to pick something other than microchip. What are my other options? Analog, Maxim, On, Renaissance, TI. And I just want one circuit. See if we can find something a little smaller. Here we go. This looks a little expensive, but it is a through hole. Let's see what it tells us. Our high, our low, RW, ground, STR, down control, up control, input. Weird, this is not even SPI, this is just like, how does this work? Storage. Interesting. Okay, so it looks like it's just almost basically sending signals. Yeah, you're using buttons to do just connect. Okay, so you can just run it high-low, force it high-low, and then that makes it go up or down. Not a huge fan of that. I wanted something SPI controlled. So let's try again. Tab series. Is there anything that like tells like the let's see here. Through hole. There's not gonna be a whole lot, so let's just see if there's anything that works. Wow, a lot of these are really expensive. There's a 3-wire serial input interface, the 3 clock, chip select, up, down. The negative edge sensitive clock requires clean transitions to avoid clocking multiple pulses into the internal down. Other suitable means. Interesting. So this is kind of expecting the same thing. It's its own custom interface, so not really what I want. All right. We might have to get creative here or just deal with it and use the one that I found earlier. There we go. All right, so that might have to become a thing. But I have to deal with the split. Maybe I just use just put the space on the board and just use the big one for the extra I/O. As annoying as it is to fit, I might be able to get away with it. insert clock, chip select. So there's just a couple. There's the shutdown and the write protect are the only two extra I/O, and I guess chip select we'll have to account for as well. Okay. So let me find that page of all those definitions again, see how this works. Because I might not have to do anything with the write protect. Maybe I can just hold it a certain direction and it'll be fine. Write protect can be enabled, disabled by two methods. For 2x1 non-volatile configuration bit. There's a lot going on here. Oh, I just realized that I hadn't turned the music back on. That'd probably be a good idea. All right, that's fixed. Indicates that the hardware shutdown pin is low. Our hardware shutdown disconnects terminal A and forces the web terminal W to terminal B while the device is in hardware shutdown. Interface is operational, so the status register may be red. It looks like the shutdown doesn't even give us that much. Huh. Interesting. And this explanation of it. Oh, here's explaining how to do it. You know, if the shutdown pin is not going to give us that much, we might as well use the smaller one because it looks like, okay, this particular circuit that they're recommending here is not actually that difficult. Devices are mad. I'm surprised they don't recommend a value for this, but for some reason I thought it would be more complicated, but that makes sense. What makes this weird then is its connection to other SPI things. Like how we do this is going to matter. I guess if we put this resistor really close to the device and everything else like normal. Well, no. All right, there is still something weird going on here that we have to think about. Okay, so what would be the best way to do this? I guess no matter what, serial data in on everything is going to be connected to this line, so it's going to receive Hold on. I'm just trying to think through this. If I have this connected to other SPIs, what's going to happen? This is definitely going to be connected to the serial. This line right here is going to be connected to the serial data in the MISO on everything, which is going to be somewhat problematic. Possibly. Oh, man. It's straightforward for if it was by itself, its own SPI, but it's not. It's connected to a bunch of others, so that this becomes a problem then. Although I guess that's already true. If so, hold on. This line is going to be driven high-low by other things anyway. So as long as the chip select is disabled, it should be fine. So then this actually works. Okay. With no special consideration. It should be okay. I'm just overthinking it. Alright, I think this part works. We need to see if it's available. Here. Give me a sec, this is running a little slow. Looks like my frame rate's struggling too, so. There it is. Oh, there is a model? Really? I was not ready for it to be that straightforward. Let's see if it has a 3D model as well. It does, okay. So I guess this works. I guess we're going with this. This is definitely one of the worst 3D models I've ever seen, but that's okay. All right. So I probably need to add this here. I seriously can't wait to see how ridiculously expensive this all is. I also like how we significantly up the complexity of this just so we can control the volume. and not just run it at max all the time. There's a better than even chance that I just get this wrong, that the speaker just doesn't work at all, but I'll at least learn something in the process. All right, so we're going to go very similar to this circuit. Maybe not use these resistors, but we are probably going to put a spot for some caps and some ferrite beads here. We can always just use jumpers if we need to, 0 ohm. And then I'll make sure I get all the voltages correct and everything. And probably include the shutdown pin, like to the logic, rather than to this, but we'll see. Actually, let me double check that part. If we do the shutdown pin, here it is. Does it use less power? Shutdown current. Max is 25 microamps, but the typical is 0.1. So that's great. That's really tiny amount of current. Should be good. Hopefully, we need to check that both of this stuff, all these things can run on 5 volts. But the SPI can run on the 3.3. That would be ideal. B5, yep. All right, we'll see on this. And then let me check the other one. The microchip parts. It might be in the other window here. What does its supply look like? Memory map and supported commands. Interesting. Excuse me. I'm trying to find electrical characteristics. Maybe that's at the beginning. Here we go. Supply voltage is 5.5. Looks like the serial interface could be lower. Puts levels. Start voltage, delay. VDD, that's fine. Leakage current. DC characteristics. Come on. Output low voltage, output high voltage. Okay, this might be an issue then. The low is fine, obviously, but the high is too much. It won't work. Unless we supply it with a lower current. But I'm worried it could pull too much. Let's see here. Digital inputs and outputs. Allows 2.7 volt digital VDD with 5 volt analog VDD. Wait, this is confusing. Okay. Five volts. This is so confusing. What is going on here? Is this 3 volt mentioned anywhere else? Just in a couple places. Let's see here. Alright, so all inputs that should be used to support high voltage on their input pin. This allows to be used in split low power and split power rail applications. Our supply. So it's our clock shut down. There's a lot going on here. It seems like it's set up so that you should be able to use a lower voltage digital stuff, but open drain with internal pull up. Oh, okay. If it's open drain, then that should be fine. Okay, I'm really confused by this, but I think it's going to work. If somebody could knows their stuff about this and can verify, that'd be awesome, but I know this is a lot. Not that one. This one? Yeah, okay. Okay. See, I want to be able to drive this chip off the 5-volt data line, but use 3.3-volt logic with it. It's just, this is not explained super well. So that is the limit, but it's not going to drive to that because it's open drain, which is fine. They have the example down here, but I still obviously don't understand everything that's going on. We're going 3-volt and 5-volt. High is 2.4, 2.4. I think this is, oh man, I think it's gonna work. So this pick MCR will drive high. Need specifications is what it says. Okay, so basically just connect it all up. It should be fine. Probably an old question, do you have a battery big enough? No, but I got around that by getting 8 batteries. So, kind of an answer to that. Let's see. SDO, which is open drain, so that's fine. We'll probably want to pull up on that then. There's just so much consideration for this. Alright, it looks like the chip select should be fine as well, so I think I'm going to roll with this. But I might put pull-ups and pull-downs on things. Just to, just to make sure it all is working appropriately, so. So I'm going to pull these two off to the side, because I'm going to need both these data sheets. And then I'll need this one as well. And then we just got to connect all of this up using that stuff, preferably to the 5 volts, which looks like it can handle. So, all right, stick with me here. So on both of them, we're probably, let's just do one at a time, actually. So let's see, for VDD, we probably want a pretty big capacitor. Try and find if there's the example application. Here we go. Yeah, 10 microfarad. Sheesh. Okay, that's huge. So did I get all that? Okay, so I got the chips in there. Let's just start putting stuff in. And then I think I'm going to do the test point things again. Okay. This is actually probably going to go over here. All right. This is going to require a lot of effort to wire up as well. It's taken us a while just to get this far, so. All right. Let me see if I have anything so far that'll work for this. If I have any 10 microfarads. I know I have ones. I thought I had a big capacitor on something, so. Yeah, I do actually. Okay. So we can use that. Here we go. All right, this goes between the voltage and here. And then obviously this gets connected out to 5 volts. I believe. Oh, shoot. This might actually need to be 3.3. No. This different voltage stuff is really annoying. Because the regulator on the teensy board is what's supplying the 3.3 volts. And it can only supply so much. So we can't do anything crazy. Okay, this does work actually. All right, yeah, we can run it off through. We can do 3.3 volt logic on the shutdown pin. Okay, so this works. All right, so we're gonna do 5 volts on this. Supply voltage. All right. All right. Out N and out P are gonna have to be their own thing, and then I need ground as well for this line. we go. And then we'll probably want to get ferrite beads and caps, so that's fine. NP and NN. All right, that needs to go according to a certain thing. All right, so 0.47 microfarads. I don't think I have something for that yet, so let's find it. In stock, active, I want cut tape. We say 0.47 microfarads. Still like 600 of them. Here. .47, .47. Okay, we want 0805 components. These. All right, something in this list. Let's see what we can do here. Maybe I could pick something from a company that we're already using. There's a lot of options, actually. This is a pretty common part. Let's see. Error? No. Really? I got something weird going on here. Let's try another one. See what happens. Maybe the whole thing's just finally broken. That's not... That's not the right picture, but the part of the stuff is at least correct. Alright, nope. Weird, it's not letting me choose from a specific library. So there's probably an error going on there. I'm just going down the list of parts. They're all pretty cheap, so... What if this is crashing my stream? Probably. Hey, this one has a part. Alright, let's just use this then. So bias, NP, outP, all of them use it. Alright, I probably need to... I don't think I've added any of these parts into my spreadsheet here, so I need to go ahead and do that. C23 is the 10 microfarad. Oh wait, no, I already have that up here, so... Alright, so this one is C24 through 26. Seven microfarad. And then I need to turn all these off. The names at least. Because that's really annoying. Even now, it's still too close to be not annoying. There we go. All right. Whoops. And the bias needs to go to the ground. Interestingly enough. All right, cool. All right, out P, out N, go to the device, shut down, NP and NN all go to the micro. Well, actually, no. NN goes to ground. And NP goes to the output of this, actually. So if I go look at that real quick. So A is one side. So that would be the in, W is the out, and B would be like ground. Okay. So the way this works, PB is going to go to ground. U is going to go to the input there. PA is going to be coming from the micro. All right, so let's run all these lines out here, and then I'll label them over here. All these I/O. And this is going to be a weird one. Okay. So for this, wow, there's a lot of control lines just coming off of this right here. All right, I guess I need a ferrite bead. What we need to filter out is actually a pretty low frequency, so we'll find something, but it'll be kind of weird. So, in stock, active, cut tape preferably, 1,000 options. Does it come in an 0805 package? Hey, it does. All right. All right, we don't need anything crazy, just something that'll filter out higher frequency noise. That's fine. I need to filter out stuff above like 1 megahertz, so it needs to be like really low frequency, and this is going to be tricky for us to find because everything is rated for like 100 megahertz. I might just have to pick something generic and see if I can find something later. All right, this is 10 cents. Let's see what it's got for us. Internet is being horrendous today. Impedance code. Yeah, so right here at the low end, it's not doing anything. It might work though. If we put that big capacitor on it too, it'll probably be all right. Y0 less than 1 amp. Standard signal speed. Packaging taped and real. Impedance code is 301. All right, at this point, I basically just have to pick something. So let's just go with that. Let's see if it's available. This is seriously having some issues right now. Let's save this to the server, see if that works. In progress, please wait. This is probably ruining my internet right now. All right, there it goes. Okay. Oh, there it is. All right, so nothing present. Let's see if we just start going down this list of items here, if we can just find one that works. Ferrite beads are probably not used that much in like hobbyist electronics. They might be, but it seems not very much, so it may be hard to find one that has like a model already made. Loading, loading, loading. Effectively what these do is filter out noise. They're kind of a special form of inductor almost. And they let a lot of current through, but they resist changes to current, or changes to voltage. So if your voltage stays the same, like 5 volts, then the current passing through the device won't be affected. Oh, look, another error. There we go. And now it works. But if your voltage is changing, sort of like an oscillation, it basically impedes that oscillation. It'll impede the current from going through and more or less filter out that oscillation. And so it's a good idea to use it, especially on something like this, where you'd want to filter out like feedback noise on a speaker circuit so we don't get any kind of feedback on it. But evidently it's really hard to find one that has some sort of model made. Let me try a different product or a different company. Bet I get an error again. Nope. Okay. Let's see here. Just trying to find one. I wish I could like... Ooh. There we go. This'll do. 3 amp, 30 mega ohm, D05. Alright, I think this works. Let me... SN1D, okay. Just double check this to make sure there's no issues with it. Oh. Pretty standard. Alright. I don't foresee any issues here, so let's use this part. Alright, one on each side. Oh wow, the symbol's huge. Might need to move this in. Really? There we go. Actually, let me move these apart a little bit. All right, and then we need to get 220 picofarad capacitors on either side there. I think that was the recommended value in this thing. Let me see if I can find that example schematic again. It wasn't in this one. It was in a different part, wasn't it? Yeah, the other part, 220 picofarad. All right, that's fine. Let me add this to the thing real quick. Kappa votes, thank you for the follow. FB1 and FB2. I didn't realize that was the ferrite bead thing. I typically just always marked them as inductors. L1, L2, such. All right. So where's our list of materials here? Let me switch these out. So we need 2 of these. FB1 to 2. And we're going to do ferrite beads. All right. Okay, so now I need to come up with the capacitors. Back to the giant list of caps. All right, in stock, active. We're getting 220 picofarad. Just want cup tape. And I want 220s. Is that a common value? It is, okay. Oh yeah, that's a really common value. All right, and then this is actually a really small capacitance for as big of a devices we're using, but oh wow, some of these are expensive. Jeez. Give me the cheap option. Here we go. Any of these will probably be fine. Let me see if I can find one that's already in the library. Stuff this small is typically used for analog electronics, so these should be safe. Bypass decoupling. That works in this scenario because it's pretty small. All right. Let's place a couple of these. All right. And then let me go ahead and add them to our materials, 27 and 28. These are 220 picofarad. So millifarad would be a millionth. Microfarad is a millifarad is a thousandth. Microfarad is a millionth. Nanofarad is a billionth, and then picofarad is a trillionth. So we're 220 trillionths of a farad. This is a really small cap. And I've actually worked with stuff much smaller than this before. So the standard unit of measurement for capacitors, the farad, is actually a surprisingly large, like 1 farad is a surprisingly large amount. To get a 1 farad cap is actually like a can-sized part. All right, so part number. So you don't see that often unless you're storing up a ton of energy on some sort of application. In college, I knew a guy who bought the capacitors that size so he can make his own railgun. And it actually worked. His bank of capacitors weighed like 50 pounds. All right. All right, so we want to rotate these and turn off the, let's go, whoops, here we go, 90. And then I think for these ferrite beads, we want to turn these names off too. I don't think we need them. You know, honestly, that would be a fun channel project, a railgun. That couldn't be that hard. I might do that. I don't know where. The thing is, this seems like designing and building it wouldn't be too bad. At least something super basic, but testing it, finding a place to test it would be. And I'm sure it's been a project that's been done to death. I might be able to find some good examples and see if I could really make it better. Just as a fun science project. I don't think I could. It would be impossible to make something actually like super dangerous or anything without spending, you know, millions of dollars, which I don't have. So, all right, bypass caps, and then we wanted test points. Where did we use test points before? Was it on the? It was on the motor. So let's go find those. These ones. All right, copy that. And we're going to put it here. Oh, didn't. Okay, didn't copy. All right, what is this? Keystone 5003. All right, we'll just place that part. Any second now. There it is. All right, drop one there and drop one there. And then get these wired up. Okay, so that part's good, and this whole circuit looks good. Now we need to do this stuff, which is really just the signal lines and then whatever capacitor goes here. So on this one, go find a example circuit again. No. I don't know that they actually gave much example on this. 0.1 microfarad was the example, okay, was the value they used for the bypass. So I believe we already use, we've got to use a 0.1 somewhere. Yeah, we do. Okay. It's this random cap. So let's place this. This part right here. By constantly, if I need capacitors of the same value, as long as I keep using the same part, this actually cuts down on the cost some, as well as making it simpler to understand the list of parts. All right, I think we decided this was powered off 5 volts as well. All right, and then we need a resistor here on the STI, SDO. Okay. So I need to know what this resistor value is. They gave an example of it here. I gotta find it though. Here it is. Okay, so this device uses the same I/O for input-output right here. So we need to put a resistor in here to make sure this is all kosher, that it all works right. Excuse me. Problem is I don't know this resistor value. And they don't seem to care to tell me an example. I suspect, well, I mean, you can definitely calculate it. This data sheet is kind of confusing because of the split voltage level things and all that. I need to know the input impedance. Or alternatively, they need to just give me an example. Higher than the voltage such that approximately VDD. Interesting. Okay. There's probably a good chance I messed this up or something. I can't make it work. Yep. All right, so they don't really give an example what this value should be. So we'll have to calculate. Here we go. What will we calculate it as? It's to ensure that VIL and VI high of the device is met. Let's find these values. Right. Hold on, somewhere we have the digital characteristics. Give me a sec. Here we are. This is probably what we care about. Let's just as the outputs. Threshold 0.45 VDD. Yeah, low is 0.2 VDD. All right, so now I need to know the impedance. Input leakage current. This will help me. 1 microamp. Okay. We can definitely supply a lot more than that. 1,000 times more. So a pretty small resistor should be fine. But how small? Would a 1K do? Because this is going to affect rise and fall time as well. If we use something too big, that's not a good idea. Yeah, I'll just go with 1K. If we do a 1K, and what's the difference on it? Oh, come on. 3 divided by 1,000. 3.3 milliamps. That's a little high, but not terrible. Like, the pin should definitely be able to do it. I think we'll be okay. Do we have a 1K? We do. All right, I'm just going to use that. And then, I guess if it doesn't work, I can always change the value on it by a different resistor, because it'll common footprint, so. There we go. All right, so for this part, we're going to use a 1K resistor that I've already found before. This one. Okay. Yep, this one. That's R32. So let me add that to my spreadsheet over here. Turn this off, okay. And then this wire needs to drop down and come out here. All right. So now I need to figure out how all this is going to connect up, and that should be fairly straightforward. which probably means it's going to be really hard. All right, so this one is going to be Mosey right here, and this one's going to be Miso. And then I got to figure out which SPI to use. Okay, it looks like the other SPI is only used once, so I will use it again for this. All right, so the way this needs to be done, well, we have some open pins which we're gonna have to use. So let's see. So shutdown, be pin 30 of the teensy, and we'll name that speaker SDB, I guess. Oh wait, no, it looks like I might already have allocated it. Yep, I did. So I've already allocated a couple of these speaker things. So SDB is just named that line. It's just named that SDB. Okay. And then if we pay attention really close here, we'll notice that these are connected incorrectly. Dang it. This one needs to go. No, POA, SDB. This is, okay, hold on. This is wrong. And just to make sure, delete this and add that. Okay. So this one is SDB. And then this one is NP. Which still doesn't fix everything, because I think we need to go do it on the teensy schematic. All right, so pin 31 is SDB. And then NP is 18. Where's that at? Here we go. All right, so those are connected. So now the other thing, which we need, the chip select is the only added line. The clock and the SDI and SDO should be the same as whatever SPI that we pick. So I need to allocate a chip select. My options are pins 30 or 34. So let me pull up the teensy pin out and see if I can understand, or see if I can figure out which one of those would be better to pick. All right, I said my options were 30 or 34. So 30 has nothing on it, and neither does 34, so it doesn't matter. Hold on. So I guess I'll just go with the first one, 30. And this needs to be, I'm going to name it pot CS. Device pin is 1. And then the device is MCP 4161-103 E_P. Okay. And then I just realized that this still had its name. Okay. All right, so this one is pot CS. And then we're going to use the SPI that we haven't used yet. So SCK1. So let me add some notes in here. All right, so Mosey Master Out Slave In 1 is pin 3. And then the same, and then the clock is pin 2. And then Miso 1. Where is that? Up here. Sorry, I'm doing this in the spreadsheet off screen, I know. I'll get back on this screen in just a second. I have a feeling we're going to have to go over this quite a lot and correct things. Just stuff that I realized that, oh, maybe we should add this or something. Just because there is so much going on. All right, that's Miso 1. All right. Like, it's easy to miss things, and there's going to be a lot of stuff that wasn't necessarily required, but is definitely good practice. And that kind of stuff is going to take a fine-tooth comb to go over it all and make sure we do the best thing we possibly can. Okay, I think all that works. So the only thing that we left to create is the pot CS, and that is on, where did we put that? Is it pin 30? Yep. Right here. Okay. All right. So that's done. Supposedly. If I go to the speaker, yep, all that's done. So if I pull up now our diagram, we've done the motor, we've done the accelerometers, we've done the neopixels, we've done the amp, speaker, we've done the buttons, power button, LCD screen, we've done all this power stuff, the driver. I think we have officially covered everything. But, you know, I don't know. Obviously, I think so. I think next time, I basically need to go through. We obviously have some extra I/O that we can use, and we'll probably make use of that. Also, we will need to go through and double check. I should go everything through. Should go through every page and make sure everything is done the best way it possibly can be. Basically, other parts that could be added just as backup stuff. So we can always add resistors to things, like we did here, and where we just don't connect them if it becomes an issue or something. Oh, you know what? On this shutdown, I think I used said to use an external pull down. I just thought of that now as we were talking about. So I'm probably going to actually do that right now. So I guess a 10K would be fine for a pull down. So let me find the 10K that we've been using. So I like how I was talking about that, and I just immediately thought of something that's like, oh yeah, we should definitely do this. Any second now. The internet is really struggling tonight. Hopefully the stream quality is not horrible. I'm probably going to get a server error, aren't I? Oh, I'm so tired. I just want to be done. This required so much thought. Yep. No, don't do that to me. Come on, let me use the part. There it is. Sheesh. All right. R33 is going to become the latest in our list of 10Ks. There's so many parts here. All right. I think that's it for tonight. I think finishing up this schematic is a huge win. I think I should, go ahead and save all this to the server and then export everything to the circuit board just so we can see it all laid out. All right, so project, validate, no issues, update PCB document. We made a lot of changes, so there's going to be quite a few things here. All right, execute changes. Looks everything looks good. And then I'm sure we'll have a lot of overlap in the circuit board thing. Ooh, yeah. Let's drop that over there and grab this and move it over here. And grab this. And this. And this. And this. And that's always like that for some reason. They must have fit the parts in here really nicely for me not to have too many conflicts. There's the ferrite beads. Make sure those are the same size as the caps we've been using. Close enough. The one test point. Where's test point 9? Oh, it's over here. With the other ferrite bead. Nice. So there's a lot going on here. So all of these components have to somehow fit on that tiny little board that's going to go inside the lightsaber. Right. What could go wrong? I was talking to somebody today about this too, and toyed with the idea of putting a fan inside this thing so we could add heat sinks and stuff like that. And I just don't know how doable that really is, but yeah, this is going to be quite fun to make all the parts and everything and try and design all this. So we're close, and we're close to being done with seeing how many parts we need. Obviously, quite a bit more to go, but good times. All right, well, thank you all for joining me tonight. This was fun, and we've got a lot more to do still, but we're close to being done on the schematic, and this is just turning into something wild, so I can't wait to see us try and put all this stuff on the board and everything. But it should be good. So anyways, I will see you all on Thursday, and hopefully we'll start fine-tuning this and figuring out anything extra that we need to add. All right, later.